Hello everyone. So today I'll be presenting a talk on privacy preserving decentralized netting, and this is joint work with my advisor Andrew Miller and my collaborator Angelo De Caro from IBM Research. So what exactly is the netting problem? So in the world of banking, a country has multiple commercial banks which accept transactions from users. For example, I can transfer $100 from my Chase bank account to my friend's Bank of America account. And all such transactions get queued up as pending transactions between the banks, which at some point needs to be settled. And what banks would like to do is settle these transactions in the most optimal way possible without going into negative final balance. So here is a pictorial representation where I have just replaced banks with parties. So you have 5 parties, and each party has some initial balance amount which we call reserve, bank reserve. And they have some pending outgoing transactions between themselves, here represented as a directed graph. What we want to do is settle some or all of these pending transactions while maintaining the following balance constraint. So we want the final balance, which is nothing but initial balance plus the sum of all the incoming settled transactions minus the sum of all outgoing transactions to be greater than 0. And we want to do this in the most optimal way possible, where optimal can be defined. For example, we want to do the maximum, we want to settle the maximum possible pending transactions. Now there is an issue. So we also care about the privacy of the participants. So for example, Alice in this diagram owes $90 to Dave, but during the settlement process, Alice doesn't want that the other participants in the settlement process should also learn that she owes $90 to Dave. What you can do is just invoke a trusted third party, such as the central bank, to mediate all these netting transactions. However, Alice doesn't trust in third parties, so we would like to use some other solution. And now Alice trusts in cryptography, so now we will use a solution based on cryptography to replace the central bank and solve this netting process in a decentralized and privacy preserving way. So here is our trusted crypto toolkit that we'll be using. So we'll use commitment schemes, zero knowledge proofs, and secure multi-party computation to solve this problem. And I'll give you a brief overview of what each of these 3 primitives are. So in a commitment scheme, you have a sender which has some private input X and a receiver. In the commit phase, sender can send a commitment string of this private input X to the receiver using some randomness R. Think of this as the sender locking up its value X inside a box and sending this box across. In the reveal phase, the sender can open its commitment value by revealing the value X and the randomness R. This is like sending the key to the box that was sent earlier. The receiver can open this box and check that the commitment was indeed valid. The guarantees of such a scheme are hiding, which means that the receiver doesn't learn about the private value during the commit phase, and binding, which means that the sender cannot open to a different value than what was committed to in the commit phase. And these commitment schemes can be based on hash functions and groups. For example, one group-based commitment scheme is Peterson commitments. Now let me tell you a bit about zero knowledge proofs. So here we have a prover with some private input X and a verifier. And let's say there is a public commitment to this value X in the sky. Now the prover claims that the value inside the commitment, the private value, is greater than 100. The verifier doesn't believe it and wants a proof of this claim. Now, a naive solution is for the prover to just open this commitment by sending the value X and the randomness R, and the verifier can check this, that X is greater than 100. But this is not zero knowledge, because in this process the verifier is indeed learning the value inside the commitment. What we would want to do is to prove this claim without revealing the values. So what you could do is have an interactive protocol between the prover and the verifier, at the end of which the verifier, using the protocol transcript pi, can run a verification algorithm which outputs either accept or reject. And this kind of interactive proofs are in fact zero knowledge, which means that the verifier doesn't learn about the private input X of the prover. These can be even made non-interactive, which means that the prover just sends a single proof to the verifiers. There is a single round of interaction. The guarantees of such a proof system are soundness, which means that if the claim that the prover is trying to prove is incorrect, then the verifier will reject with high probability. Completeness, which means that if the claim is correct, then the verifier will always accept. And zero knowledge, which means that the proof doesn't leak anything beyond the validity of the claim that is being proved. In particular, it hides the private input X of the prover from the verifier. Now, let me introduce you to the third ingredient, which is secure multi-party computation. And I would like to demonstrate this using a very simple use case. So, imagine we have 4 parties and they have some private inputs, which are, let's say, their private salaries that they earn at a company, and they would like to compute the total value of their salary. Obviously, no one wants to reveal their private salaries to each other. So, what they can do is call a trusted third party and send their inputs, their salaries, to this party, which then computes the sum and forwards this sum to all other parties. This is a secure solution, but we would like to remove the need for such a trusted third party. And this is exactly what MPC lets you do. MPC lets you compute a function on private inputs of parties without needing a trusted third party. It lets you emulate this process using a distributed protocol, where, for example, Alice can use his input and split it up into 4 pieces, which are called secret shares, and then send these shares across to all other parties. Each of these individual shares hides the actual input X. Similarly, Bob, Charlie, and Dave can do the same. At the end, they will hold secret shares of the salaries of all participants. Each party will hold secret shares of all other participants. What they can do is add up these shares locally to arrive at a secret share of the sum of the salaries, which they can then broadcast to each other and then open this, reconstruct these shares to obtain the final sum. At the end of this process, it is ensured that only the sum of the salary is being revealed apart and nothing else. The MPC protocol specifically that we will rely on will tolerate a minority of corruptions, which means that if there are n parties and the adversary corrupts no more than n by 3 of the participants, then it cannot compromise the privacy of the honest parties. It cannot even interfere with the correctness of the output of the function that is being computed. And we also have robustness, which means that the adversary cannot prevent honest parties from receiving the output. For example, even if adversary terminates, like for example in this figure, even if one of the party, Dave, terminates the protocol in between, all other 3 participants will still receive the output of the function. Now, let us get back to the settlement problem now that we have the toolkits. So, recall that each party had some balance amount and some pending outgoing transactions, and they wanted to settle these transactions subject to the balance constraint. So, first we have some observations. Note that the net pending transaction at each party is basically the sum of its outgoing pending transaction minus the sum of its incoming pending transactions. Each party can locally check whether they have sufficient balance to net all their incident transactions by checking whether this expression balance amount minus net pending transaction is greater than 0 or not. And if so, we can easily perform these checks via zero knowledge proofs, specifically zero knowledge range proofs, which are extremely efficient and non-interactive. For example, Alice can post a zero knowledge proof on a public bulletin board attesting to this fact that his balance amount minus his net pending transaction is greater than 0. However, these checks might not always succeed. Why? Because some parties might indeed have low balance and might not have sufficient balance to net all their pending transactions, or the adversary might even send incorrect proofs in some cases. Our fallback solution is to use a fault-tolerant MPC in such scenarios to settle the optimal set of pending transactions. And this kind of MPC, this fault-tolerant MPC, as I mentioned earlier, ensures privacy, correctness, and robustness. So now I'll demonstrate what our protocol is by just abstracting away the actual values. So here I've represented the balances in capital L letters with the subscript representing the participant, and the pending transactions are represented by small letter t. And so T sub AB represents the pending transaction from Alice to Bob, and so forth in the other edges. So first we have a setup phase where each party has some initial balance, right? Capital L, A is the initial balance of Alice, and capital LB is the initial balance of Bob, and so forth. So first we have commitments to initial balance amounts being generated on the bulletin board, and this is a setup phase. For example, the central bank can do this to bootstrap the system and then leave the system. And note that what we use is additively homomorphic commitments. So for example, Peterson commitments are additively homomorphic, which means that you can combine the commitments to two values and generate a commitment to a value which is the sum of the underlying values. Additionally, we have the secret shares of each party's balance being generated and distributed across all other parties. So this is the setup phase, and now we move to the actual decentralized protocol. So first part is the input phase. So in this phase, parties start with some pending transactions, outgoing pending transactions that they want to settle. So Alice has two sets of outgoing pending transactions, one for Bob and one for Charlie, and Bob and Charlie have their own outgoing transactions. Now, as a first step, Alice posts commitments to its outgoing transactions that it wants to settle on the bulletin board, and so does Bob and Charlie. Additionally, all participants generate secret shares to their transaction values, outgoing transaction values that they want to settle, and distribute it across all other parties. So we have commitments to transaction values and secret shares to same transaction values. Okay, so now the inputs are distributed. Now we move to the first phase, which is the optimistic ZK phase. In this phase, we won't even make use of secret shares at all. We would just use commitments that were generated and try to solve the problem. So as I mentioned, each party can locally check whether they have sufficient balance to net all their incident transactions. So for example, Alice can add its initial balance with its outgoing pending transactions minus the incoming pending transactions and check whether the expression is greater than 0 or not. And if so, it can post a zero knowledge proof on the bulletin board for this fact. Note that we already have commitments to initial balance and commitments to outgoing and incoming transaction on the bulletin board. That can be used to derive a commitment to the final balance because these commitments are additively homomorphic, and we can prove a statement on those commitments asserting this zero knowledge range proof. And so every party can do the same, and at the end each party verifies whether all the proofs posted on the bulletin board are in fact valid. If all the proofs are valid, parties can locally update their secret shares by adding and subtracting, and these addition, because it is linear, can be done locally, and also update the commitments to final balance. So we have commitments to initial balance, commitments to outgoing and incoming transaction. Those can be used to derive commitments to final balance. Now, as I mentioned earlier, this optimistic ZK phase might not always succeed. And in those scenarios, we have the fallback MPC phase. And in this phase, we will actually make use of the secret shares that were distributed across the parties, secret shares to balances and outgoing pending transaction. So we have the secret shares. So whenever I have those square brackets, those represent secret shares. That's just the notation. So we have secret shares of each party's balances and secret shares of all the outgoing transactions. So every party holds a secret share to every other party's balances and every other party's outgoing transactions. As a first step, we run an MPC balance check protocol, which basically checks whether all parties have sufficient balance to net all their outgoing transactions. And this is needed because in the zero knowledge proof phase, some parties might just drop out and not complete the protocol even if there was sufficient balance to net all transactions. So in this phase, we check whether this part is correct, and if so, if the MPC check passes, which means the participants have sufficient balance to net all their incident transactions, we can locally compute secret shares of final balance for each party because of the additive nature of the shares, and also generate a commitment to the final balance on the bulletin board. However, if on running this balance check procedure, we get to know that the check fails, which means that some bank in the system did not have sufficient balance to net all its incident transactions, then we run an MPC optimization step, where we use these secret shares in order to run an optimization algorithm. Specifically, we make use of Karmarkar optimization algorithm, which is a linear programming algorithm, to determine the optimal subset of transaction values that can be settled. At the end of this MPC phase, what we have as the output is secret share of each party's updated final balance, which are represented by L prime, and secret shares of the pending transaction amount that couldn't be settled, which are represented by T prime. This is just the output of the MPC protocol. And along with this, we also have as outputs the commitments to the same final balances and the pending transaction amounts. And everything that falls below the dotted line on the bulletin board will serve as inputs for the next epoch of the settlement process. So this is now how the transaction graph will look like for the next epoch of the settlement. And we will run the same procedure all over again for the next epoch. For evaluation, we implemented the netting optimization process, the Karmarkar optimization, using 3 different algorithms, the naive and FIFO and Karmarkar. Naive is basically we just check whether every party has sufficient balance to net all their transactions, and if so, we do the settlement, otherwise we do not settle any transaction. FIFO is the process of settlement which was in the prior FC work of decentralized privacy preserving netting. And here the transactions are settled based on a predetermined ordering. So, the transactions which come first are settled first. And Karmarkar is a linear programming based solution of optimization. We measured the performance of settlement in terms of percentage settlement, which is basically the ratio of the transaction amount settled to the total transaction amount that was input to the protocol. We also implemented and benchmarked the communication and computation cost of our MPC based solution of Karmarkar using the MP Speeds MPC platform. So, here is one evaluation. So, this graph shows the percentage settlement on the y-axis and the distribution that we are generating the transactions from on the x-axis. So, we sampled the distribution from a normal distribution, sampled the transaction from a normal distribution with mean as $500 and standard deviation of varying amounts plotted on the x-axis. As we see that the green line, which is our optimization algorithm that we implemented, has much higher settlement percentage compared to the naive and the FIFO settlements. When we evaluate the cost of our MPC procedure in MPC, we plotted it for 3 different parameters: CPU time, communication cost, and number of MPC rounds. We saw that as the number of banks increase in the system, all these 3 parameters increase considerably. And the issue is the Karmarkar optimization algorithm that we run for this netting optimization has the order of n to the 6 running time, where n is the number of banks. So, it is this limits the applicability to only small number of banks. But all this implementation was done in a single threaded application. So, there is much avenue for optimization by using multi-threaded implementations, and Karmarkar algorithm is mostly based on matrix operations. So, there is avenue for parallelization and reducing these CPU time costs. Future work is to, as I said, improve the cost, communication and computation of the MPC optimization procedure. And a second work is to add auditability to the MPC phase. Basically, as I said, the MPC security hinges on the fact that an honest majority of the participants is maintained throughout the protocol. But what might happen in a real world that the honest majority assumption is violated. In that case, what we would like is that even if the honest majority assumption is violated, the correctness of the output should still remain. Otherwise, for example, what might happen is if all banks try to collude together, they can inflate the currency supply of the system. So, we would like to stop that kind of scenario. And you can possibly do this using auditable MPC, a notion already known in literature. Thanks.